Okay, I guess I can start. So indeed, as Beth was saying, I changed the title of my talk because I thought I want to report on some more recent results. Namely, I like to talk on non-perturbative superpotentials and in relation to D terms in Orientfold compactifications. But before I really start, I like to first to say that I feel indeed very much honored and privileged to be here with all of you, and in particular to be here with you, Shimon and Eliezer. I always really enjoyed discussing and talking with you. Also, we didn't write any common papers together, so hopefully this will be in the future. But I always enjoyed the discussions with you, both on an academic and scientific and also on a personal level. So thank you for this. Moreover, I like to remind that I think it was said already several times here that Eliezer and Shimon made numerous profound contributions to field and string theory, and also contributions that are important for this talk. So I'd like to mention in particular the relation between gauge theories and D-branes, respectively supergravity, duality symmetries, non-perturbative effects in supersymmetric field theories, which will become important later during the talk, and of course quantum cosmology, quantum black holes, and many other nice and important things. So the outline of my talk will be about the following. First of all, I like to recall a few facts about perturbative Orientfold compactifications. After that, I will proceed to non-perturbative superpotentials, and there's a lot of recent related work on that subject. And finally, I will explain that there is, first of all, an apparent clash between non-perturbative superpotentials and D terms, which are important for uplifting, but if you look more carefully, one can resolve this apparent clash. So, what is the structure of Orientfold compactifications? So, at the perturbative level, they contain, first, one has to choose a closed string, 6-dimensional background geometry, say, in the simplest case, a torus, an Orientfold, a Clavier space, or also generalized spaces with some torsion. You choose some closed string background fluxes, like the Neville-Schwartz 3-form flux, several Ramond fluxes, and also, in general, some so-called geometrical flux contributions. We choose, in general, space-time filling D-branes, so the dimension of the space-time branes is 4 plus p, and hence they are wrapped around internal p-dimensional cycles. And these space-time filling branes give rise to open string matter fields. And finally, due to reasons of charge conservation, one has also to choose some Orientfold 4 plus p planes, which are, as I said, necessary for so-called tadpole cancellation. So in the geometrical large radius regime, which is the regime I want to discuss during my talk, in type 2a, the D-branes are, the space-time filling branes are special Lagrangian submanifolds, namely the 6 branes, which are wrapped on 3 cycles, and these 3 cycles, the various 3 cycles intersect at particular angles inside the compact space. In type 2b, we deal with D3, D5, D7, and D9 branes. The D5 branes wrap complex lines, the D7 branes are wrapped around 4-dimensional submanifolds, so-called divisors, and the D9 branes wrap the entire compact space, but by some reason I will restrict the discussion on the D3 and the D7 case. And where we had the angles on the type 2a case, the type 2b branes are now equipped with so-called gauge bundles, and using the mirror symmetry, say a la Strominger-Yauch-Zaslav, one can say that these two branes neatly map onto each other. So this is a very neat example also of duality symmetries. So we have a picture like this, where also the Orientfold is exhibited, which is a kind of reflection symmetry along some submanifold in the compact space. Or I can show you another picture here. We have the Calabi-Yau space, and say at some corner we have branes which are responsible for the standard model. These are the so-called standard model branes. And in some other corner we have, in general, other branes, which are the so-called hidden sector branes. And yes, these branes could also talk to each other and give rise to other effects like supersymmetry breaking in the observable sector. Okay, as an example, I like to choose now the type 2A intersecting brane. So to be a little bit more specific, we choose so-called stacks of D6 branes which are wrapped around Calabi-Yau 3 cycles. For the 3 cycles, we can choose a certain homology basis called alpha I and beta I, where the index I runs from 1 to h to 1, the Hodge number h to 1. So far, therefore, we have the following geometrical input data. Namely, first of all, we choose k of these stacks, and each stack is characterized by a certain number NA, the number of branes in each stack. And then, moreover, these branes can wrap the 3 cycles, the various 3 cycles, not only one time, but several times. So we have integer wrapping numbers, which I denote by xia and yia around the alpha I and beta I cycles. So in general, our stack A is denoted by this kind of cycle pi A, which is a linear combination of the basis cycles. So if we specify now this geometrical input data, we get out some physical output data. And the basic physical output data are first the open string 4-dimensional gauge group, which in the simplest case is a product of unitary groups of this form. And moreover, 4-dimensional massless fermions from the open strings which sit precisely at the intersection points. And now there's a nice formula to compute the degeneracy, namely one can compute the intersection number between the A cycle and the B cycle. This is a topological invariant. It's given by this simple expression, and this counts, so to say, the number of chiral fermions. So this is a kind of family index, say, in the standard model. So here's a picture which shows this again. In the simplest case, the massless fermions are in the bifundamental representation. And now in order to get a fully consistent string compactification, one has to satisfy 3 kinds of consistency conditions. First, there is a Ramond-Ramond-Tedpol cancellation, which tells you that the Ramond charges of the branes and the Orientfold images has to be balanced precisely by the Ramond charges of the Orientfold plane. The second condition, if we insist on space-time supersymmetry, is the supersymmetry condition, which tells you that the cycle PA must be a special Lagrangian submanifold, or perhaps in more geometrical terms, it fixes essentially or determines the intersection angles of the various branes or cycle. And finally, there are also additional conditions due to K-theory. So one can now put all this, in principle, if you choose a particular background on a computer, you get equations over integer numbers, essentially, namely over these wrapping numbers and the number of branes in each stack. And it turns out, I think this is a nice result, that say you choose a particular closed string background, you get a large but finite number of possible brane embeddings. So you can really go through with a computer through all the brane embeddings. This is what one can call D-brane statistics. This was done by our group, but also by the group of Bert Schellekens in Amsterdam, not in the geometrical region, but using so-called Gettner models. So you can really classify models based on this statistic and also see what is a fraction of models which has, say, nice fermiological properties. So in a particular class of models, we found out that, say, the likelihood to find the standard model is 1 in a billion, and we investigated this for several classes of models, and Bert et al. Investigated this for different classes of models. So this is essentially how you construct the models and how you can also make statistics with them. The next step is to compute the perturbative effective action, which means essentially that we have to compute open and closed string amplitudes in conformal field theory, say at the tree-level disk. And I just remind you, for the open string fields, we have the gauge fields and the meta fields, which are in the supersymmetric model chiral fields. In the closed string sector, we have essentially the moduli, the Kähler moduli denoted by Ti, the complex structure moduli denoted by and also the dilaton field S. So you compute the string amplitudes, and at the end you want to get out the effective action. So I show you here some of the building blocks of the n=1 supergravity effective action. Namely, first you have the kinetic energy for the gauge fields multiplied by a function of the moduli, which is a gauge kinetic function. Then you have a perturbative tree-level superpotential, which is cubic in the meta fields in general, again with a moduli-dependent function in front of it. May also contain some flux part in flux compactification, which is entirely determined by the moduli. Then you have a Kähler potential, again for the moduli and also for the meta fields. And having this superpotential and Kähler potential, you can compute, for example, physical observables like the Yukawa couplings, and you need in fact the Kähler potential in order to get the right normalization for the meta fields as it is known. Okay, so again we now try to do this for the type 2a intersecting D6 branes, and I give you some of the basic results. We have the complex structure moduli, as I said, and these are given by these general expressions. The real part of the holomorphic 3 from omega integrated over some of the cycles times the integral over the C3 field. The Kähler moduli are defined in this way. And then, for example, you can compute first the tree-level gauge kinetic function. And it turns out that it is a linear combination of the dilaton and, say, in a toroidal model where you have three complex structures, of the three complex structure fields, where the coefficients of this linear combination are determined by the various wrapping numbers n and m. So it is obvious that each of the branes or each of the gauge group have in general a different tree-level gauge kinetic function or a different gauge coupling constant because these wrapping numbers are different. So it is not like in the heterotic string where there's a universal gauge coupling constant given by the dilaton, but here it is different for each dex determined by this kind of expression. You can proceed, you can compute the meta-Kähler potential, and here you find some interesting expressions in terms of gamma functions. These gamma functions, to explain a little bit better, has an argument, the intersection angle theta, where theta is a function which still depends on the complex structure modulus. So this is a little bit more complicated function of the complex structure moduli, and then there are also several scaling factors with some parameters. I do not want to discuss this in any more detail, but remember perhaps this first factor, this square root of the gamma functions in front of, and you get it, for example, by computing 4-point scattering amplitudes with 2 moduli and 2 meta fields. Yes, please.
I'm not sure I'm understanding where the fluxes are in all of these. If these computations are done with the fluxes set equal to 0?
Yes, essentially it's right. This is not a talk on flux compactification really, and indeed to perform the computations, because it's probably not possible to do it with non-vanishing Ramon fluxes. In these computations the fluxes are set to 0. That's right. Mm-hmm. There is no flux background here at the moment. So we can proceed after doing the tree-level computations and compute, say, also one-loop corrections to the effective action, say, to the gauge coupling constants. These are given by one-loop annulus or cylinder diagrams. Say we have this kind of worldsheet topology with two gauge field insertions at the boundary. And what you will see that quite in general, you expect an holomorphic contribution to the real part of an holomorphic function to the gauge kinetic function at one loop, but possibly also some non-holomorphic contributions. So let me explain this a little bit in more detail. If you take also into account the massless states, you get a log m string square over mu square times the beta function of the corresponding gauge group, something which plus something which we call the gauge threshold contributions, which depend on the moduli. So if we first look at the holomorphic piece, one can argue by Peccei-Quinn symmetry that the tree-level gauge kinetic function, as I have shown you, depends on the S field, the dilaton, and the complex structure, whereas the one-loop contribution depends on the Keller moduli, entirely on the Keller moduli in this way, and finally the non-perturbative contributions could depend both on the complex structure and the Keller moduli. So again, let's do now this computation for the intersecting branes. You get for the so-called n equals 2 sectors this kind of expression, but let me maybe focus on the genuine n equal 1 sectors. And here you will see that the gauge threshold corrections are again given by an expression which we have encountered already before, a very similar expression, namely this ratio of gamma functions. But observe that this ratio of gamma functions is entirely non-holomorphic. It depends on the complex structure modular field as a non-holomorphic function. So this is a entirely non-holomorphic function, which means that in these models the one-loop holomorphic gauge kinetic function is absent. So what is the origin of this non-holomorphic contribution in the one-loop effective action? Namely, these non-holomorphic parts are due to Keller anomalies or more general sigma model anomalies. They are again due to the wave function renormalization. And I do not want to enter the subject now. You can now compute triangle diagrams involving matter fields. And you will see, indeed, there is a useful check that all the factors, I do not really explain this equation now, but just to give you an expression, that if you collect all the factors which come from the Keller metric and compute from the running of the massless fields the contribution to the one loop gauge to the one loop threshold correction, you precisely get this non-holomorphic contribution. So this works out nicely, and this is, I think, a good check that the string computation fits nicely also with the corresponding field theory computation. Okay, so this was, in short, part of the perturbative story, and now let me proceed to discuss non-perturbative parts of the effective action, namely the non-perturbative superpotential. And just to motivate this, if we go back for a second to the perturbative effective action, usually it contains global U1 symmetries, also global U1 symmetries from massive U1s, which are broken essentially by the Stückelberg mechanism, but U1 always perturbatively remains as a global symmetry, and these global symmetries very often forbid certain couplings, like Yukawa couplings or neutrino masses. So in many models you have a problem that there are no Majorana-like neutrino masses perturbatively, and one likes to know whether they can be generated non-perturbatively. Moreover, if you now would enter the subject of flux compactification, you will see that perturbatively in general also not all moduli are stabilized. In general you need non-perturbative effects. And also I think for space-time supersymmetry breaking, non-perturbative effects are important. So the task is to include non-perturbative instanton corrections to the effective field theory action. This is, yes please. Yes, I will remark on this later on. You could also now compute the instanton corrections to the gauge coupling constant. And if you do it correctly, it should come out as a holomorphic expression. Of course, the non-holomorphic one-loop piece will not disappear. This is there, and it is consistent. This is a subtle subject, because this is a subject of so-called sigma model anomalies, because these anomalies generate non-local terms in the effective action. And from the first sight, indeed, you would think this is not consistent with n=1 supergravity, but the statement of n=1 supergravity concerns the so-called Wilsonian effective action from the massive fields. This is indeed holomorphic, but if you integrate also over the masses fields... Excuse me? Yes, yes, yeah, yes. Mm-hmm. Yes. Yes, right. This is also one way of phrasing it. I think this is one way of phrasing it, perhaps in a bit more technical terms, but it's true. Mm-hmm. Mm-hmm. The physical effective action contains these non-holomorphic pieces. So, if you want to know the precise, if you want to know the value of the one-loop corrected gauge coupling constant, you have to take them into account, because they are modular dependent. It's clear. This was also true in the heterotic string. There were also always, in this case, like log t plus t bar terms in the gauge coupling constant at one loop, which are non-holomorphic, but which are important for the actual computation. Okay, so we want to include now the non-perturbative instanton corrections. This is, of course, not a new subject, but I think there are recent nice developments how to perform actual concrete calculations, and this is also what I want to present to you first. So here is a list of references on string instanton corrections. These can break axionic shift symmetries and hence also the global U1 symmetries, and therefore you can expect that they generate couplings which are perturbatively forbidden. So they generate new meta couplings. They can generate new moduli dependent terms in the superpotential, and hence they are also important for the vacuum structure. And possibly they break also supersymmetry. And this is also a point I like to stress. In string theory, these string instanton effects in general also go beyond gauge theory non-perturbative effects. And the reason why this is so will be hopefully also clear in a second. So as I've mentioned already, it is possible to compute these string corrections, these string instanton corrections from CFT by very similar techniques as we have computed the perturbative action, and this may sound surprising, but I will show you why. So in a way, we not only can guess them from field theory and take over results from field theory, but we can compute them in string theory from scratch and even test or reproduce some of the old field theory results, as I will show you. Okay, so there are two kinds of instantons. First, the worldsheet instantons, which go like E exponential of the volume, the Kähler form over alpha prime, and they are still tree-level in the conformal field theory, so these are not really the ones which we are interested in now. And then there are space-time instantons, which go like e to the minus 1 over gs, or also combine things. And if you look closely, the effects which I will compute contain both the worldsheet instantons, but more importantly, the space-time instantons. So what are these Euclidean D-branes, these string instantons? These are in contrast to the D-branes which we had before, which were always space-time filling. These can be described by non-space-time filling dp, or therefore called also EP Euclidean p-branes, which are wrapped around internal p plus 1 dimensional cycles. And the one comes here because we also wrap the time direction of the brane around the internal cycle, and therefore they are called Euclidean branes. So they are a snapshot in space-time and sit entirely in this internal spatial directions. Again, we can make the same list as before. In type 2a, again, we deal with spatial Lagrangian submanifolds, and if you do this now trivial count, we deal with E2 branes on 3 cycles. In type 2b, we have points, E-1, E1 branes, complex lines, dividers, E3 branes, and the entire Calabi-Yau space, which is then in Euclidean E5 branes, and there should be again related by mirror symmetry, by duality symmetry. Okay. A short remark: since the beam-mu field is modeled out on the Orientfold, we do not discuss here the Neveu-Schwarz 5 instantons, which were also discussed before in the literature. So now, to be a little more technical, when we deal with these Euclidean branes, and in a way, I'd like to point out the space-time filling branes, it was essentially up to us to include them or not to include them. Of course, they had to satisfy the Tedpol equations, but these branes are not restricted by the Ramond-Tedpol equations because they are not space-time filling, and regardless what you do, they are there. You have to include them and to see what is their contribution to the effective action. So they are there, and they are hence very important for the couplings and for the vacuum structure of the theory. So what one has to do, in more technical terms, we have to integrate over all bosonic and fermionic zero modes which are localized on these Euclidean branes. And if you do now the zero mode count if you do the zero mode count in the supersymmetric effective action correctly, you will see that not all instantons indeed contribute to specific terms in the effective action. So very roughly, if you look at F terms, superpotentials, the EP brane has to be half BPS, so it has to contain 2 fermionic zero modes. And if you look at D terms, scalar potentials and stuff like this, the Euclidean branes break all 4 supersymmetries, which means hence that they should have 4 fermionic zero modes. So in order to be specific, again, we will consider in the following the contribution of an E2 instanton to the superpotential in type 2a Orientifolds. But the mirror picture type 2b, I think, could be also easily done. So to again recall, the E2 brane wraps now a 3 cycle, which we call Xi. The cycles of the space-time filling branes are called pi. In order to have a different notation, the cycles of the instanton branes are called Xi. Of the Calabi-Yau space, and it's, I think, clear from the beginning that the non-perturbative superpotential is proportional to the exponential of minus the instanton action. And the instanton action itself is proportional essentially to the volume of this 3 cycle, so essentially it is proportional to this expression here, and you see in this expression here the string length on the one hand, so we deal with worldsheet instantons, and also the string coupling constant GS, which means that we deal in particular with space-time instantons. And it's also understandable, perhaps it becomes clear why also worldsheet instantons are important here. The instanton corresponds to a local minimum of the string action, which means that the cycle Xi has to be volume minimizing, so again it has to be a supersymmetric Lagrangian 3 cycle. In general, this instanton action is not invariant under U1 gauge shifts, which are shifts in this C3 field, and this is important also to understand why certain U1 symmetries will be broken by the instanton action, which will, I think, more clear also later on. But, of course, the entire superpotential, should be U1 invariant. So after having seen that this exponent is not U1 invariant, one has to compensate for it, which means that in general the expression is not as simple, but there will appear a bunch of a product of meta fields in the non-perturbative superpotentials. The meta fields also have a particular U1 charge, and the charge of the meta fields, the U1 charge of the meta fields, together with the shift here in the instanton action, will make the whole expression again U1 invariant. So if you imagine that these meta fields are, say, neutrinos, right-handed neutrinos, whose mass violates the U1 symmetry, the U1 is restored precisely by this additional term. And this is the reason why non-perturbatively you can have matter field couplings which a priori perturbatively seem to be forbidden. Yes? No, it is a shift in the imaginary part of the corresponding complex field.
But this field is a scalar in 4 dimensions.
It is a chiral field in 4 dimensions, that is right.
So why do you call it a gauge?
Well, because it is related, yes, it mixes with, you can compute a triangle diagram, I will show you, say with, or better say, you can compute a diagram which mixes the U1 with this particular field, and therefore this field, as I will show you later, the shift is nothing else than a particular gauge transformation. So these fields, no, it is a Stückelbett field, I would call it, which makes the corresponding U1 massive. So these U1s which are involved here are those which are not necessarily anomalous. In most of the cases they are anomalous, but they get a mass due to this mixing with the chiral field. Again, we knew this from the heterotic string, where they are mixing between the S field and also U1s. But here it occurs that there's not only one of those chiral fields in general and one of those U1s, but there can be more. There can be several of the masses U1s in the type 1.
This one gauge symmetry has already been hit. And what is left between the 0 mode and the global symmetry?
Well, maybe you can say. Maybe you hold for a second. I will show you later on when we come to the d-terms, and this is really related also to the question of Fourier plus d-terms, to see here really how the symmetries act, and perhaps then it becomes more clear. Okay. So now, as it was shown recently by several groups, in particular by Blumenhang, Svetic, and Weigand, these non-perturbative couplings can be calculated again now in open string conformal field theory, and these U1 selection rules will follow from the fermionic 0 modes. So in fact, I will demonstrate this in a local setup. So we consider the following quiver diagram. So the quiver contains three cycles on the Calabi-Yau space. Say first the cycle pi a, which gives rise to the gauge group, say UNC by NC, the 6 branes on the stack A. Then say we have another stack of branes which I call the flavor branes, which in principle gives rise also to another gauge group, can be only one of it. There are these flavor branes, and the flavor branes and the gauge branes usually intersect each other, and at the intersection point we have the massless chiral fields phi and phi tilde, which are physical fields. In addition, now we have our Euclidean instanton, which is wrapped around a cycle psi, which a priori must not be or is not necessarily identical with these two cycles here. And again, we have now open strings which are stretched among the instanton cycle and the other two cycles. So these are again open string fields located at the intersection points. However, since this cycle is not space-time fillings, these open string fields are not really physical fields. However, they correspond to 0 modes, and you have to integrate over these 0 modes to eliminate them and to get the effective action of the physical fields phi. So more concretely, we have 0 modes lambda, which I denote by lambda, which are the flavor, if you wish, the flavor 0 modes, and also 0 modes between the color group beta and B. And here I have included also some bosonic 0 modes, which are in general massive, but you could also see, yeah, this is what we get. This I have already explained in words. Now we have the gauge group, the gauge fields on the UNC stack, and we have the bifundamental meta fields, and again the number of them is determined by a chiral index, by an intersection number, times the number of branes here, because these are bifundamental. What the point I want to make now is that we can have two different situations, namely, before I come to this, I like to discuss the zero mode structure a little bit more. We have this B1 psi fermionic zero modes coming from the open strings, starting and ending also on the cycle psi. And in general, one can say that these must be absent or soaked up by closed string modes, by additional closed string modes, by fluxes. So in order to not enter the discussion of the slugs, if you want to assume that the cycle is rigid, that these zero modes are absent, but in specific models this can cause some problem, and to solve the problem, I think one has to invoke other closed string fluxes. We have the bifundamental fermionic zero modes lambda and lambda f, and again they have now Dirichlet-Neumann boundary conditions in 4 dimensions, and this in particular means that there are no physical fields, and again the number of them is given by a certain intersection number. And finally we have also the bifundamental bosonic fermionic zero modes in the color sector. Now, and this is I think important, there are two possible cases. The first case is that the two-brane wraps a 3-cycle which is different from the gauge group 3-cycle. This is what one would call a genuine string instanton, namely an instanton which is only present in string theory but not in field theory, because in field theory these other cycles are really completely decoupled. But however, if you determine the vacuum structure of your compactification, also these really stringy instantons are very important. Of course, the other case is that the E2-brane wraps precisely the same 3-cycle as the gauge group C-cycle, and then the E2-brane precisely corresponds to a, say, good old gauge instanton, and in this case we have these 4 NC additional bosonic zero modes, which I have denoted before by B and B tilde. So depending which case we are discussing, you have to deal also with these additional zero modes. Okay, so now you might ask yourself whether this procedure really works, whether one can perform these CFT computations with this kind of unphysical gauge fields. Yes, Nati? Yes.
Wrap these other cycles. So imagine you generalize your problem a little bit and wrap these other cycles K branes. Then this group, I'm asking this is the question.
With physical branes, with space-time filling branes, do you mean, or not? Yes.
Then these will be instantaneous in the new K gauge.
Right.
And then if they K to 0, will you get the same answer?
I think it's not really up to you whether you wrap also K space-time filling branes around the other cycle, because now they contribute to the Ramond-Tedpol equations, and it's not clear whether you can just throw them in and still your consistency equations are satisfied. Okay, so if you now are skeptical with this method, one good test, I think, is to compute the one instanton Veneziano, Jankelowitz, Affleck-Dine, Seiberg superpotential, which is very well known in field theory, using these stringy methods, and to see whether we get precisely this good old field theory result. So this is one thing we did in Munich. So I just briefly show you the computation. So we want to compute such essentially such a contribution to the charged matter field superpotential, where this in general is not really a product but a determinant over fields. But I simplify now a little bit, and maybe I skip now the technical details. You can look it up in our paper. Essentially, you have to compute this rather big looking integral with the various zero modes fields, and I will show you briefly. You also have to, you have to include also the one loop vacuum amplitude and the disk vacuum amplitude, and then also you have to compute the various correlators of the matter fields, of the physical matter fields, and of the zero mode matter fields. So this expression is rather sketchy. It is even more complicated in the actual calculation, and moreover, you have to be careful because the integration over the zero modes fields is not unconstrained. There is a constraint, namely the ADHM constraint, which also have to be taken into account. So here are a few of these pieces which appear in the amplitude. The vacuum disk is nothing else than the instant on action, which I have shown you before. You get a vacuum one loop annulus amplitude contribution. And here, this is, I think, interesting. This contribution precisely reproduces the threshold correction, which at one loop level, which I have discussed before. And this should indeed agree with the holomorphic one loop contribution from the massive string states. In a way, you get an intriguing relation, which we have not really checked, but in a way one can conjecture this relation on the diagrammatical level, that the instanton amplitude, which is this kind of annulus, corresponds to the non-instanton amplitude with two of the gauge fields insertion, and I think this relation is correct. We have 3-point disk amplitudes between one matter field and two zero mode fields, so two fermions and one boson, like the Yukawa coupling. You do the zero mode integration. Then you have another 4-point amplitude which you have to compute. Again, you do the zero mode computation. And this bosonic zero mode computation, this is maybe important to mention, brings down the phi's in the numerator now in the denominator. And here I have written it as a determinant. So if yes, please.
This procedure for handling the zero modes, is this something you infer from field theory, or is there a CFT rationale?
I think if one is honest, it is in a way motivated by dealing also with the zero modes in field theory. In string theory, one has to, of course, consider the various U1 charges, and U1 charge conservation is very important here. But for example, I think how to involve also this additional constraint, the ADHM constraint, this is clearly also motivated from field theory. Okay, so perhaps you might object, then it is not completely unexpected that. No, but okay, somebody might object that it's not completely unexpected that one gets the field theory result, but I think things conspire in a very nice way. So if you put everything together, indeed we obtain the Veneziano-Jankelowitz, Affleck-Dine-Seilberg non-perturbative superpotential. You can perform the field theory limit really in a strict sense, decoupling all the scales correctly, and then you get this result here. And one thing I like to mention, we had this constraint. This constraint tells you, since we are computing a one instanton amplitude, that NF must be NC minus 1. The number of flavor brains is now coupled to the number of color brains. In this way, only in this case, the zero mode comes out correctly because we are computing a one loop, a one instanton amplitude. And one can also now generalize this for Orientfolds, for other gauge groups like SON. Here the constraint is like this, or for symplectic groups where the constraint correctly comes out like this. So you might think about possible generalizations. Can we also enter the region where NF is smaller than NC minus 1, which would correspond to Gaugino condensation? Here one would have to compute the so-called fractional instanton amplitude, and we are thinking about how perhaps it can be done. Or what about the problem of non-rigid cycles, which is also very important for model building? Maybe I mentioned it at the end. From the field theory point of view, these non-rigid cycles correspond to gauge theories with adjoint chiral fields in the gauge group. And these spoil the non-perturbative superpotentials, as it is known from the field theory. So these adjoint chiral fields must get a mass by fluxes. The degeneracy must be lifted, and therefore one needs the fluxes for these cases. Yes?
In the case where you did the computation, you were in type plane of intersecting plane 26, right?
Yes.
In that case, all the cycles are not rigid.
Correct. Therefore, you have to choose other cycles or turn on the fluxes if you want to apply this for these models. I have described it for you as a local setup. I have shown you this quiver of these three different cycles. Now you have to embed this again into a compact model to see whether this contributes. There was a paper by, I think you did a paper on this, and other people like Bianchi. And one has to see how it comes out now in models. And I will also mention the paper by Bercelic and Uranga and Ibanez, who consider this in the Gebler model context. But your question is, of course, correct. Okay, so now, after this discussion on the superpotentials, I will switch gears a little bit. Yes, please. Mm-hmm. No, we got it from making the right decoupling limit by identifying alpha prime and the string mass in the correct way and identifying it as a QCD scale lambda. Okay. So I just want to mention in short the KKT proposal for moduli stabilization. In this KKT proposal consists out of two steps, namely, now I do not discuss it in detail. First step is the fixing of all moduli by fluxes and non-perturbative effects, which gives rise to gives rise to supersymmetric ADS vacuum. And this was investigated for example, in blown-up orbifolds. And in the second step, because ADS is a vacuum with negative cosmological constant, one should think about mechanisms to lift the minimum of the potential to a positive de Sitter vacuum, and there are certain proposals in the literature, like adding anti-D3 branes or the 7 branes with so-called F-flux. And indeed, this later mechanism is the one which I want to discuss now in the last 10 minutes or so, namely this mechanism or this introduction of the 7 branes is nothing else than turning on non-vanishing D terms. Of course, there's a subtle issue which I like to mention, I think which was pointed out by Hans-Peter Nilles et al., that in order to make this work, one has, in a way, to change also the F terms which we had before, because there's a kind of no-go theorem that non-vanishing D terms imply also non-vanishing F terms. And to do it is a rather subtle issue. So, for example, you could think about also to have the uplift entirely in the F term sector, which also people consider, and I think Hans-Peter Nilles also has a nice paper on that. So this is one issue, but there's another issue, because at first sight there seems to be a clash between the KKLT superpotential and the existence of D terms, and this again is related to these anomalous shift symmetries which we already discussed before. So let me briefly introduce the D terms. A D term potential in the scalar potential arises from the existence of a gauge shift symmetry, and perhaps this is now related to Nati's question 50 minutes ago or so. We have a U1 gauge vector superfield which transforms like this under U1 transformations. And now this field mixes, say in the Keller potential, with a chiral field which we denote by Tc in this way. And the mixing coefficient is denoted by a constant, the so-called delta Green-Schwarz coefficient. So in order to keep the Keller potential of this form U1 invariant, it is clear that the Tc is also to shift under the U1, and therefore the T field, its imaginary part, is charged, so the axion shifts. And this field now, if you only focus on the axionic part, appears now in the gauge covariant derivative in this way. If you expand out this action, you get this d mu ac square plus q a mu term, and the mixing, the charge of the axionic field is precisely given by the delta Green-Schwarz field. And hopefully this answers Nati's question from before. Okay. Moreover, this mixing now leads to the following. Fayopoulos determined the effective action, namely, if you perform this derivative of the scalar potential with respect to the vector superfield, you get the parameter xi, and the D-term potential is essentially nothing else than the square of the xi Fayopoulos, or in our parameters written like this. Or in other words, the D-term potential, in more general, arises from the standard expression. It is given as a square of d. The D-term, d is the derivative of the scalar potential multiplied by a so-called killing vector field, which is constant in our case, and it corresponds to the gauge shift symmetry. So now, due to this non-invariance, there are two non-U1F invariant terms in the action. Namely, first, if there is a gauge group U1C times SUNC with coupling, with gauge kinetic function or coupling real part of TC, then the term trace FC, wedge FC times imaginary part of TC is not U1 invariant, obviously. So this might look as a problem. Or, which is related, if this gauge symmetry induces now a gaugino condensate and a perturbative superpotential of this form, again the TC shifts under the gauge symmetry, again the U1 flavor, the U1F gauge symmetry is non-invariant. However, it is known how both non-invariances can be cancelled by the same mechanism, namely we introduce now NF meta fields, phi I, which are charged, which carry particular charge, both under the U1 and also under the SUNC. So if you wish, they are bifundamental. And then the first non-invariance is cancelled by a anomalous triangle, which is a Green-Schwarz mechanism. I'm afraid my time is running away. And the second non-invariance is cancelled by including these fields in the non-perturbative superpotential by the well-known Affleck-Dine-Seiberg determinant. So the non-perturbative superpotential from gaugino condensation is indeed U1F invariant if the Green-Schwarz coefficient, and this is a non-trivial statement, at least in field theory, precisely matches up the number of flavor fields, because you see each field phi carries 1 unit of U1 charge, and the determinant contains essentially a factor phi to the NF. So the NF is important and has to be precisely coincide with the delta Green-Schwarz. And then at the end we get this D-term potential. So since time is running short, I want only to indicate very briefly how this is now realized in string theory. And in string theory, in type 1 strings, this is essentially realized by the very same setup as we had before, namely we have two stacks of physical branes. I now switch by some reason from type 2A to type 2B, so we are discussing the 7 branes which intersect each other. So we have these bifundamental meta fields, and the aim is now to compute microscopically the D-term in this kind of setup to see whether the mixing coefficient in the D-term, which I have called delta Green-Schwarz, precisely matches up the number of master chiral fields NF which we have to introduce. So maybe I jump over these steps. One can do it by dimensional reduction and by essentially dimensional reducing the Born-Infeld action on the 7 branes. And indeed, if you do it at the end of the day, you will see that the delta Green-Schwarz coefficient, which was a priori not a topological intersection number is indeed again given by the intersection number of the branes with respect to each other. So indeed, the delta Green-Schwarz is nothing else than the fermion number, and things really nicely match up here in this, again, local brane setup. So, in other words, the superpotential, the ADS superpotential is indeed consistent with the D term. In principle, it would enable us now to study the uplift procedure from the ADS minimum to the visitor vacuum. Okay, so what is my conclusion on the Euclidean D-branes? They allow us to compute the non-perturbative gauge theory ADS superpotential. You can also go beyond non-perturbative gauge theory effects. They are relevant for the study of the string landscape, as I have briefly explained. They also introduce perturbatively forbidden couplings like Majorana masses, and there's a a nice paper where this was systematically studied in a class of models, namely in Gebner models. And indeed, if I read the paper correctly, there are still these problems of the zero modes, which do not precisely come out as you want to have them to generate the Majorana masses. And there's also some work in progress, namely we also want to compute the non-perturbative instanton corrections now to the gauge kinetic functions in type 2 Orientfolds. So let me stop here. My last conclusion is that I just want to say, dear Eliezer and dear Shimon, thank you very much and all the best for the coming years. Nothing, I think. For NF bigger than NC, we are... yes. Sure. Maybe I appreciate your question now. You should perhaps now compute different kind of couplings where the selection rules are just right. And indeed, this is something which is on the agenda, but not yet done. But I think it's certainly interesting. As I said, you get all kinds of new couplings now. In principle, as long as the zero mode counting comes out correctly, not only the ADS Veneziano-Jankelowitz superpotential. The fractional instanton case, as far as I understand, is the case where F is smaller than NC minus 1. And the other case is not really conventionally called a fractional instanton. Yeah, this question was essentially asked before. From CFT, from worldsheet, we take the correlators of the zero modes with the other fields, which are important to get after integrating over the zero modes the right dependence on the charged field. So here the correlators, the 3-point function and the 4-point function which I've shown you is essential. The other part, the zero mode integration, is, I think, more field theory like inspired, I would say. Well, in some cases, it is indeed, this is work of Carlos van Brooyen and others, how fluxes lift zero modes. So this was done in particular for the Euclidean D3 instantons, which are wrapped around divisors to see whether they contribute to the KKT superpotential. So, and you can set up rules what type of fluxes, whether they are 2,1 or what is the hot structure of the fluxes and so on, to see how the zero modes are lifted. So there's partial work done, but I think it's not very systematic, and moreover, for these other type of couplings like Majorana masses, there is no study so far, I think.
Okay, I think there are no more questions, so let's thank people again.
You're welcome. Thank you.
Getting it from gun and taking it.
Yeah.